In this lecture, what I want to do is prove this thing called the Fundamental Theorem of Arithmetic. And I don't know if maybe you haven't heard it explicitly called this before, but I'm sure you've used this before. All right, what the Fundamental Theorem of Arithmetic says is that every integer greater than 1 can be written uniquely as a product of prime numbers, give or take the order the factors are arranged. Okay, in other words, 3 times 2 and 2 times 3, yeah, we're going to call those the same thing. Right? We're not going to worry about the order of the numbers. And you've used this before. You used this all the way back in elementary school when you're doing things like finding the least common denominator of 2 fractions. You know, the first step is to take, let's say we want to do 1/12 plus 2/15, right? The first step in finding that least common denominator is to find the prime factorization of each of the denominators, and that's where this theorem comes in, right? This theorem is saying 2 things. First, it's saying that prime factorization has to exist, right? You can absolutely do this for every number. And the second is saying that this prime factorization is unique, right? There's never going to be more than one way to do it. All right, so this is what we want to prove in this lecture. And then I'll talk a little bit at the end about why this is significant, both to number theory and to computer science. So before we can do that, I have a little lemma here. Now we talked about lemmas briefly a little bit before. Remember, a lemma is a theorem in its own right, but it's one that's maybe it doesn't take the proof is short and is not necessarily very interesting in its own right. It's more interesting because it is really useful in proving something else, right? And that's what we're going to see here, right? This is going to be an important part of our proof of the fundamental theorem of algebra. Of arithmetic, excuse me. So what do we know? If P is prime and P divides the product of 2 numbers, then P either divides the first number or the second number, right? So to kind of see what's going on here, notice that this is not necessarily true if P is not prime. All right, for example, if A is equal to 4 and B is equal to 9, then 4 times 9 is divisible by 6, even though 6 does not divide 4 and does not divide 9. Right, because in this case, right, 6 is 2 times 3, and the 2 we can reduce with the 4, and the 3 we can reduce with the 9. You kind of split it up, right? Reduce each factor of that non-prime number with a different one of the A and the B. If that denominator is prime, then what this is saying is that it all has to go into 1. Right? We can't split it up this way. All right, so how can we do this? Right? Well, here's what I'm going to do. Assume that P does not divide A. All right, so what I'm going to do is I'm going to prove that this forces P to divide B. Right? In other words, if it doesn't divide 1, it has to divide the other. Okay, so if P does not divide A, then they have no common factors other than 1. Right? So then the greatest common divisor of P and A is 1. So what does that mean? Well, here I'm going to bring out Bezout's identity, right, from earlier lecture, right? By Bezout's identity, there exist integers m and n such that m times p plus n times a is equal to 1. Good. Okay. Now here. What do I want? I got to get B into this somehow, right? Because I want to talk about divisibility of B. So let's do that. Let's multiply both sides by B, right? If I do that, what do I get? This becomes BMP plus BNA, and that has to equal 1. Okay, good. Now, excuse me, that has to equal B. All right, so now notice what we've got going on here, right? First, P divides BMP, obviously, right? BM is an integer, right? BMP is an integer. Okay, now the other side, this is also true, right? And P divides, let me rewrite this. Let me rearrange these. A, B, N, right? I know P divides A, B, N because, remember up here, P divides A, B. All right, well, so what does this tell me then? This tells me that P divides the sum. P divides BMP plus BNA, but now we're just going to substitute, right? Substitute B in there. Therefore, P divides B, and that's what I needed to show. All right, so now that finishes the proof, right? Now just kind of hold on to this, right? Kind of hold on to this. We're gonna use this in the next slide or two here when we actually start getting into proving the fundamental theorem of arithmetic. So there's really two things we need to prove here in this theorem, right? The first thing we need to prove is that this prime factorization exists. And the second thing we have to prove is that this prime factorization is unique, right? And existence may seem a little weird to you in this case. How can something not have a prime factorization, right? You found the prime factorization of God. I don't even want to know how many numbers over the course of dealing with fractions and denominators like we talked about earlier. But this is the kind of thing mathematicians are careful about. We don't want to make assumptions, because what you've done so far in algebra classes and math classes back in elementary school, you've looked at a lot of examples, right? You've seen a lot of examples of situations where a number does have this prime factorization, but that's not a proof. Right? Looking at specific examples does not constitute a proof of something. You have to use that universal instantiation. You have to work with the general case, right? Because the point I would make about your experience here is that you've probably done this pretty much exclusively for numbers that are relatively small. How do you know that your process is not going to break down somehow when numbers start to get really big, like hundreds of digits big, right? Or 100 isn't even really all that big a number. Say thousands or tens of thousands of digits. You don't really know for sure until you've proved it. Okay, now I don't plan to make a habit of this, but we're not going to prove this right now. Proving this requires a technique called strong induction, which is a little beyond where we are right this minute. We're actually going to talk about proofs by induction later on, but it's a little past where we are right now. So I'm going to set aside this proof of existence for the time being and focus on proving uniqueness, because this is something we can approach at this point in the class, and it illustrates an interesting type of proof. How do we show that something is unique? Right. Well, here's how we do it. All right. So I'm going to say let we're talking about the factorization of an integer, right? So I'm going to say let P be let P be an integer, and let P equal P sub 1 times P sub 2 times all the way out here to P sub k, right? And let P equal Q sub 1 times Q sub 2 times, again, all the way out here to Q sub m, where P sub I and Q sub I are all prime. Okay, so in other words, I've written P as the product of a bunch of prime numbers in two different ways, right? And what I need to show is that these two ways are the same, right? In other words, well, let's start with this. Let's say, look, let's let P1 times P2 times out to P sub k equal Q1 times Q2 out to Q sub m, right? And I know I can do this because they both equal P, right? It's just substitution. Okay, now one thing I do want to point out, but before we dig any deeper into this, you notice how I used different final indexes. I use K on the left and M on the right. I am not assuming that these two lists are the same size. Maybe one has more than the other. I don't know. Haven't proved it yet. Right, so here's what I'm going to do. Here's where I'm going to apply Euclid's lemma. Right, I'm going to divide both sides of this by P sub 1. Right, so then what happens? The left side is just P sub 2 times all these P's out to P sub k. What happens over here on the right? Well, this is where, like I said, this is where Euclid's lemma is going to come in. Because P sub 1 is prime, I know that it has to divide one of these other prime numbers up here. Okay, assume that it's Q sub 1. If it's not, then rearrange your numbers. Okay, rearrange the numbers so that the one that matches P sub 1 is in front and cancel it. So when I do that, I'm left with Q2 times all these numbers out to Q sub m. Do it again. Divide both sides by P2, then P3, then P4. Keep going all the way to the end until you've canceled out all of the P sub k's. Right, so I'm a little out of room. Let's jump up here. I'm going to say dot, dot, dot. You do all these divisions. The left side is now equal to 1. What is the right side equal to? Well, we have two possibilities. One is the right side is equal to 1. Right? And if that's the case, then every P sub I had a matching Q sub I, and the two factorizations were the same. Right? Another possibility is that there are numbers left over. Right? We have Q, let's say m minus 1, Q sub m. Let's say there were 2. Doesn't, if there's more, we're going to have the same problem. Right? So now here we do have a problem. We have the product of two prime numbers that's equal to 1. No, there are no such prime numbers. Right? Remember, prime numbers are strictly greater than 1. So this case can't happen. Right? That's impossible. So what happened then? Every P has to have a matching Q over there on that list. And if every P has a matching Q and every Q has a matching P, then these two things, those two expressions, are actually the same expression. And there is, in fact, only one way to write our original P as a product of prime numbers. Okay, so I say what's next here, but I also want to talk for a minute about why this is important. Mathematicians like to reduce things. Right, we like to say, well, look, instead of talking about this really big group of objects, maybe we can just talk about this smaller group of objects instead. Right, and that's kind of what we've done here. Right, we've shown that there's a really tight relationship between composite numbers and prime numbers, and that kind of thing is useful to us because there will be situations here in number theory and in computer science and fields like cryptography where instead of trying to talk about all integers, the fundamental theorem of arithmetic is going to let us say, well, look, let's just talk about prime numbers. And because every other number is a product of unique prime numbers, well, then this applies to all those other numbers as well. Right? So this fundamental theorem of arithmetic, which I'm sorry, I know I keep saying algebra, the fundamental theorem of arithmetic gives us a way to in some instances, make problems simpler by letting us look at a smaller group of numbers. Okay, so where are we going to go next? This is the end of our discussion of prime numbers. In the next section here, We're going to talk about something called congruences. Right? And congruences are kind of neat because they let us do this again. They let us do the same thing where instead of talking about a big group of numbers, it gives us a way to reduce them down to a smaller set of numbers. And they're also, congruences are also a very useful tool in cryptography. So we're going to talk about that a little bit as well.